So in a previous video, I showed that the number e, Euler's constant, was indeed an irrational number. So today I want to show that it's a transcendental number. I'd like to thank Squarespace for sponsoring this video. What do I mean by a transcendental number? I mean that it is not the root of an integer polynomial. So let's look at some examples of some numbers that are not transcendental. In other words, they are algebraic, just to give us a feel for the importance of this proof. First of all, the square root of 2 is clearly an algebraic number. It's the root of an integer polynomial. That integer polynomial is x squared minus 2. Notice if we evaluate x squared minus 2 at the square root of 2, we clearly get 0. Furthermore, the square root of 3 plus the square root of 5 is an algebraic number. And there's a nice trick to build the polynomial for which this is a root of. We can do that by setting x equal to this number, and then doing just algebraic manipulations on that until we get a polynomial equation. So first of all, we could square this, square both sides. We'll get x squared as 3 plus root 5. We'll move the 3 over and we'll square it again. And notice we've got a polynomial equation with integer coefficients whose solution is this guy right here. Furthermore, by a very, very important theorem of Galois, the insolvability of the quintic, we know that degree 5 polynomials and higher may not have solutions using radicals. And so this is probably an example of such a polynomial, but its roots are algebraic. So we don't just need square roots and stuff to build an algebraic number. It could be roots of a crazy polynomial. Okay, so now that's out of the way. What I'd like to do is start looking at some important objects for this proof. The first of which is a number which I'll call m. And it's defined to be 1 over p minus 1 factorial times the integral from 0 to infinity of x to the p minus 1. And then we have x minus 1 all the way up to x minus n to the p power times e to the minus x dx. You might say, well, what are n and p? But that'll become clear when we look at the proof. They'll be defined within the proof. Then we have complementary numbers, m sub k and epsilon sub k. Notice that m sub k is almost exactly the same. The two things that we change are a multiplication by e to the k and starting the integral at k instead of 0. Furthermore, epsilon sub k is also almost the same. The two things we change are, again, the multiplication by e to the k. And then starting at 0, like we did in the first case, but ending at k. Now let's notice from some elementary properties of integrals, if we add m sub k and epsilon sub k, these two integrals fuse together into this one, meaning we have the following equation down here. M sub k plus epsilon sub k equals e to the k times m, which we'll use during the proof. Now, one more thing before we get started, and that is the proof that I'm going to present is fairly classic. You can find it in a lot of different places. But maybe a good reference would be my favorite calculus book, which is by Spivak. So if you've learned calculus in a course, but maybe you want to learn it better, that's a good second book to read to learn calculus maybe for your final time before moving on to more advanced mathematics. Okay, now let's jump into the proof. I'm excited to be working with Squarespace for this video. So personally, I've been using Squarespace for 6 or 7 years for my personal academic website, which you can check out at www.michael-penn.net. Squarespace makes good design easy to come by with beautiful templates that allow drag and drop construction. And you can access the backend and coding if you'd like to have even more flexibility. In fact, there's an easy way to integrate LaTeX into Squarespace for equations. You can check examples of that on my website. I think it does it beautifully. Many academic websites are stuck in the 1990s, especially math websites. And I think it's time for us to step up and have a little bit better design. And that can be easily done with Squarespace. You don't have to be like a design guru to make a beautiful website using this product. Check out squarespace.com for a free trial. And when you're ready to launch, go to squarespace.com/michaelpenn to save 10% off your first purchase of a website or a domain. So what are you waiting for? I think now is a great time to build your own website. And Squarespace is a really great place to do it. And if you do so with my link, you'll be really helping the channel. And now back to math. Okay, so now that we've kind of reviewed what a transcendental number is and we've set up our special objects, let's maybe jump into the proof. Okay, so let's do it. How are we going to do this? Well, we're going to use a mathematician's favorite trick, and that is a contradiction. So we're going to work by way of contradiction. So that means we want to start by supposing that, in fact, E is not a transcendental number. So in other words, it's something called an algebraic number, and then see that that causes some sort of problem. So what does it mean to me, an algebraic number? It means that it is the root of an integer polynomial. In other words, a polynomial with integer coefficients. So here's what we'll do. Let's suppose we have integers a0, a1, all the way up to an, such that, well, first of all, a0 is not equal to 0. That'll be important. We can always choose a0 not to be equal to 0 just by, well, I'm going to write down the polynomial and it will be clear. Okay, such that a0 is not equal to 0, and we have an e to the n plus an minus 1 e to the n minus 1 plus plus a1e plus a0 is equal to 0. So notice if a0 is equal to 0, then that means 0 would be a root of that. We could factor an x out, and then e would be a root of a lower degree polynomial. So in fact here, this n is maybe the smallest degree of a polynomial for which e is a root of that polynomial. Okay, well, let's notice that this is a polynomial evaluated at e. It's the polynomial where we've replaced all of these e's with x's. So that's where our n comes from. It's the degree of the polynomial for which e is a root of via this contradictory type of argument. Okay, great. Now you might say, well, what is this p? Well, since we're using the letter p, it's probably a prime, but what rules does this prime satisfy? Well, we're going to go over it right now, and this may not seem obvious while we're looking at it, but it will be obvious as we move forward with our argument. So let's take a prime. Like I said, I'll call it p to fit in line with this notation over here, such that p satisfies two conditions, but I can wrap those conditions into one part. So p is larger than the maximum of the number n, so the degree of this polynomial, and the absolute value of a naught. That means it's larger than n and it's larger than a naught. And we're able to do this because there are an infinite number of primes, so we can always find a larger prime if we wanted to. And notice this condition right here gives us a pretty quick kind of corollary, and that is p cannot divide n. In other words, n is not a multiple of p. That's because p is bigger than n. And n cannot divide a naught. Again, that's because p is larger than the absolute value of a naught. Recall that a naught is an integer, but something that is larger cannot divide this number. So we have these two failures of divisibility. Okay, so now that we've got this, I'm going to introduce some more numbers. So let's define C0, C1, C2, all the way up to CNP. So these are going to be all integers. And how are they defined? Well, they're going to be defined by the expansion of a certain polynomial. What polynomial? Well, let's go over it right now. It's the expansion of this polynomial that's within all of these integrals. So it'll be x minus 1 times x minus 2 all the way up to x minus n all to the p power. So I'm going to expand this like one step at a time so that we know something about divisibility among these numbers. So first off, we can expand the inside here. Notice that'll give us x to the n plus a bunch of stuff that we indeed don't actually care about. And then that will end with plus or minus n factorial. Then we have that all to the p. And obviously it will be a plus if we have an even n, and it'll be a minus if we have an odd n, but we actually don't care if it's plus or minus. We can just leave it like that. Now if we exponentiate that to the p, we'll have x to the np plus dot 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 plus, now we'll have n factorial to the p. And that's going to be a plus or a minus at the end. And this is the polynomial whose expansion will define these coefficients. So I'm going to write this as the sum as n goes from, as maybe j goes from 0 up to n times p of cjx to the j. So let's observe that we know two values of the c's pretty easily, and we don't actually need the rest of them. So let's notice that CNP is equal to 1. That's the coefficient of x to the NP. And then C0 is equal to plus minus n factorial to the p power. And now, while we're at it, I want to point out that this n factorial, this plus minus n factorial to the p power, is not divisible by our prime p. And it's not divisible by our prime p because p does not divide n. So if it doesn't divide n and it's in fact larger than n, it won't divide anything smaller than n, so it won't divide n factorial. That means it won't divide the pth power of n factorial. Okay, so now that we've got this set up, we want to investigate something about this capital M number. Okay, so let's keep in mind these numbers Cj that we looked at on the last board, and let's use them to argue something about this number M. So I'm going to take this number M, instead of rewriting it like this with this integral, I'm going to rewrite it with the way we expanded this polynomial. So this will be 1 over p minus 1 factorial. That comes from this. And then we'll have the sum as j goes from 0 up to n times p of cj. And then I'll have my integral from 0 up to infinity of x to the j times x to the p minus 1. So that'll be x to the j plus p minus 1. And then we've got this e to the minus x dx. Okay, so again, that's just using those ways that we expanded this polynomial here with these numbers c sub j, using the definition of this m. There's not much going on here. Okay, so next up, I'm going to use a fairly standard result about this integral right here. So this is related to the factorial, or more generally, the gamma function. And it's well known that if we have something like x to the r times e to the minus x dx, and we integrate it from 0 to infinity, we get r factorial. So that means here we'll get j plus p minus 1 factorial. That'll be the value of this entire integral. So that means this whole thing is going to collapse to the sum as j goes from 0 up to infinity. And then we'll have c sub j, and then j plus p minus 1 factorial over p minus 1 factorial. Now let's notice that something important is happening at the j equals 0 term. Because at the j equals 0 term, this numerator and denominator cancel. But if j is larger than 0, they don't cancel. So let's keep that in mind and maybe extract the j equals 0 term and then analyze this thing a little bit more. So for the j equals 0 term, we get c sub 0. On the last board, we noted that that was plus minus n factorial to the p power. And then we'll have plus, our sum is now from 1 to n times p. This should be n times p. And then we'll have cj. And now I'll cancel all of those that I can. So that means this is a descending product at j plus p minus 1, ending at the number p. So the very important thing here is that it ends at the number p. That makes this whole thing a sum of things that are multiples of p. In other words, this guy right here is a multiple of p. But let's recall from something that we saw on the last board, or some argument that we previously made, this guy right here is not a multiple of p. So m is the sum of something that is not a multiple of p, and n is a multiple of p. So that tells us that in the end, p does not divide m. So in other words, m is not a multiple of p. And that's the main takeaway about the structure of m that we need right now. We just got done showing that this number m was not a multiple of p. In other words, p does not divide m. Now we're going to start to analyze this number m sub k. And I should say k here could really be any natural number, but for us, we're going to take it between 1 and n, just for the purposes of our proof moving forward. Okay, so let's look at this guy. So we've got m sub k. I'm just going to copy this over. This is going to be e to the k over p minus 1 factorial. Then we've got our integral from k up to infinity of x to the p minus 1, this big polynomial that is all to the p power times e to the minus x dx. So the trick here is we want to do a change of variables so that we integrate from 0 to infinity instead of k to infinity, just to make this thing work out a little bit nicer. And the change of variables that will make that happen is u equals x minus k, which means x is equal to u plus k, and thus dx is just du. So now performing our change of variables is not too bad. Notice that this e to the k will combine with this e to the minus x and give us an e to the minus u. So that's good. Then we'll have something that looks like this. 1 over p minus 1 factorial. Then we'll have the integral from 0 to infinity. Because when x is k, u is equal to 0. We have u plus k all to the p power. And then we have this descending product starting at u plus k minus 1 and ending at u plus k minus n. That's all to the p power e to the minus u du. So the most important thing happening here is because of the fact that k is between 1 and n, somewhere in this descending product, we subtract exactly k. But at that moment, we have this number u here. That means when we expand out this entire polynomial, there will be no constant term. In fact, everything will be a multiple of u to the p. Okay, so keeping that in mind, we can do a similar expansion to what we did on a previous step with those cj numbers to form some dj numbers. So that'll give us something like this. The sum, as n goes from 1 to n times p, like I said, here we'll start at 1 instead of 0 because we've got this u term here. Everything is non-constant. And then we'll have, like I said, these numbers d times j, and then p plus 1 minus j factorial over p minus 1 factorial. So something that looks like that. Now the important thing here is because we don't have that constant term, recall that constant term was not divisible by p, but everything else was. That means that all of this is a multiple of p. So what does that tell us? The big result from this step is that p divides m times k. That's going to be true for all k between 1 and n. And now let's move on. Okay, now we want to jump back into the polynomial equation that is satisfied by e towards our contradiction and interject this observation right here. So let's recall that we had a sub n e to the n plus all the way down to a1 e plus a0 equals 0. Okay, now from here, what I'll do is I'll put in all of these values of e sub k just for each of these cases. So that'll give me something like this. We have a sub n, and then instead of e sub n, I'll write m sub n plus epsilon sub n over m, just solving that thing for m. And then that's going to go all the way down to this thing right here. We have m sub 1 over epsilon sub 1 over m plus a naught is equal to 0. Next up, we'll multiply through by m, and that'll give us maybe the most important equation towards our contradiction. And that is a sub n times mn plus epsilon n plus all the way down to a1. I left off this a1 times m1 plus epsilon 1 plus m times a naught is equal to 0. Now I'll pull this apart into the m parts and the epsilon parts. That'll give us something like an mn plus all the way down to a1 m1 plus a0 m. Again, that's all the m parts. And then we'll have plus an epsilon n plus all the way down to a1 epsilon 1. That's equal to 0. So next up, let's recall that this guy right here is not a multiple of p, whereas this guy right here is a multiple of p. So that means if we add them together, these are not a multiple of p. Okay, but what does that tell us? Well, 0 is a multiple of p. That tells us that this cannot be 0. Again, because 0 is a multiple of p, and we showed that this was not a multiple of p. So we have an mn plus all the way down to a naught m is not equal to 0, but it is an integer. Notice that each of these three things are integers by our construction. Okay, so now let's keep that in mind, and we'll start working towards our contradiction. We're working towards the end now. On the very last step, we showed that mn plus all the way down to a naught m was not equal to 0. It was a non-zero integer. Whereas the sum of that number together with an epsilon n all the way down to a1 epsilon 1 was equal to 0. And that was by our assumption that E was not transcendental, which is working towards our contradiction. So now we want to investigate this number right here and see that this thing is problematic, or these two things together are problematic. So let's look at the size of one of these epsilon k's. So we have the absolute value of epsilon k. So that's going to be equal to, just rewriting this definition right here, e to the k over p minus 1 factorial. And then the absolute value of the integral from 0 to k of x to the p minus 1. And then we have x minus 1 multiplied all the way to x minus n. That's all to the p power times e to the minus x dx. Now I'm going to do a couple of steps all at once. I'm going to move my absolute value inside of the integral. That'll produce an inequality. I'm going to change this k to an n. That'll be an inequality in the same direction. I'll change this x to an n. Again, an inequality in the same direction. And then this p minus 1 to a p, again, an inequality in the same direction. And then furthermore, I'll factor this out while I'm at it. So that'll give me something like this. So this is less than or equal to e to the k, n to the p, again, that's from this exchange right here, over p minus 1 factorial. Then I have my integral from 0 up to n, and now it's going to be the absolute value of x minus 1 all the way up to x minus n. That's raised to the p power e to the minus x dx. Now notice that the absolute value of this polynomial is a continuous function on a bounded domain. That means it achieves its maximum. So let's call that maximum a. So I'll just put these absolute values in yellow so we can see where this is coming from. And a is going to be the maximum of this. So that does not include the p power, but includes everything else. So that means I can again push the inequality in the same direction. And upon doing that, I can pull the a to the p out of this. So that means I'm going to have epsilon to the k, and then I'll have n times a to the p, smushing those together, and then over p minus 1 factorial. And then the integral from 0 up to n of e to the minus x dx. But while we're at it, we're going to add one more thing to this inequality that, again, pushes the inequality in the same direction, and that is to change this upper bound. Instead of stopping at n, we'll stop at infinity. Now, this integral right here is pretty easy to calculate, and it's just equal to the number 1. So that means we have all of this at this moment is equal to e to the k, n times a, all to the p power. This is going to be over p minus 1 factorial. Now notice we have an exponential in the numerator. We have something like a factorial in the denominator. Let's recall that using limits, an factorial will always beat or will win over an exponential. Recall that n and a are constants. There may be complicated constants, especially a, but they are just constants. So that means if we let p go to infinity, this will all go towards 0. And we're allowed to let p go towards infinity because there are an infinite number of primes. So this limit is happening over the primes. Okay, so if each of these is going to 0, then that means this whole clump is going to 0. And that's actually how we'll finish this proof off on the next board. So we've done a lot of work to get here, but we're finally ready to finish this off. I'm going to change this but statement to an and statement because those are really the same. I have this is true and this is true. But now applying a result that is from the last board where we showed that all of those epsilon k's go to 0, well, really we showed their absolute value went to 0, so that means they go to 0 by the squeeze theorem. That means that all of this right here goes to 0 by the additive nature of the limit. But if all of that goes to 0, that means we have a sub n, m sub n, all the way up to a sub 0, m is actually equal to 0. So let's look at our and statement. We have that this object is not equal to 0 and it is equal to 0. But that's a very, very clear contradiction. Now, what did we contradict? Well, our very beginning assumption at the beginning of this whole game, which was that e was not a transcendental number. So that means that the conclusion here is that e is indeed a transcendental number. And that's a good place to stop.